Item number 1. In a plant nursery, the owner thinks that the lengths of seedlings in a box sprayed with a new kind of fertilizer has an average height of 26 centimeters after 3 days and a standard deviation of 10 centimeters. One researcher randomly selected 80 such seedlings and calculated the mean height to be 20 centimeters and the standard deviation was 10 centimeters. Will you conduct a one-tailed test or a two-tailed test? Proceed the test using alpha equals 0.05. For the first step, we're going to describe the population parameter of interest. The parameter of interest is the mean of the population where the sample comes from. Step 2 is formulate the null hypothesis and alternative hypothesis. Our null hypothesis is our population mean is equal to 26, while our alternative hypothesis is our population mean is not equivalent to 26. Next, we're going to check the assumptions. Is the sample size large enough for the CLT to apply? The answer is yes, because the n is equivalent to 80. Next is, do small samples come from normally distributed populations? Samples are assumed to come from normally distributed parent populations. And lastly, are the samples selected randomly? The answer would be yes. Next, we're going to choose a significant level for alpha. Is the test two-tailed or one-tailed? It is a two-tailed test. Get the critical values from the test statistic table. With the 95% confidence level, our critical value would be plus minus 1.96. Next, we're going to establish the critical regions. So as we can see here in the bell curve, the critical area is shaded. Next, we are going to compute the test statistic. So we are going to use this formula right here. So if we substitute that with our given, we have 20 minus 26 over 10 over the square root of 80. We will then get the test statistic of negative 5.37. For our sixth step, we're going to state the decision rule. Reject the null hypothesis if the computed test statistic is less than or equal to the negative critical value, or if the computed test statistic is greater than or equal to the positive critical value. Otherwise, do not reject or accept the null hypothesis. For our next step, based on the decision rule, decide whether to reject or to accept the null hypothesis and interpret the result. Since our test statistic is equal to negative 5.37, and if we simply take a look at the shaded region, it is reasonable to conclude to reject the null hypothesis. With this, there is enough evidence to reject the null hypothesis, and the population mean is different than 26 centimeters at 0.05 significance level. There is a significant difference between the sample mean and the population mean. Thus, the claim of the researcher is not true.
For item number 2, I will be answering the following questions. For question A, is hypothesis testing an efficient way of solving problems? Why? My answer is yes. Hypothesis testing is an efficient way on solving different kinds of problems. In order to know or determine the significance of a certain info or data to ascertain which statement is best supported by the sample data, it will help on with or with not the data is likely to be rejected or accepted. For question B, compare and contrast estimating parameter values and hypothesis testing. My answer is, estimating parameter values is a part of statistics that involves estimating the parameters of a distribution using the sample data. The purpose of a parameter estimation is to extract numerical values of the parameter from a sample in which the numerical values of the parameter are located. While with hypothesis testing, it draws conclusions about a topic using the data from the sample. Using sample data, the hypothesis testing technique determines whether the null should be rejected or accepted, more like an assumption for the population parameter. For question C, when is it appropriate to use the t-distribution in testing a hypothesis about a population mean? The t-distribution is used when data is normally distributed. This should be used when the standard population mean is unknown, and it is appropriate to use the t-distribution when the sample size is small or lesser than 30. Lastly, for question D, in what ways are the distributions of the z and t statistic alike? How do they differ? The main similarity of these both are they are both used to test a hypothesis. Both curves are symmetrical about the mean and are positioned in the center of the distribution. Thus, they never touch the x-axis. They both differ through their sample sizes, wherein z-tests are used when the sample size is large or n is greater than 13, while t-tests are most likely to have smaller sample sizes or n is less than 30. Both methods assume a normal distribution of the data, but the z-tests are most useful when the standard deviation is known.
This is our problem number 3. An experimental study was conducted by a researcher to determine if a new time slot has an effect on the performance of pupils in mathematics. So 15 randomly selected learners participated in the study. Toward the end of the investigation, a standardized assessment was conducted. In the standardization of the test, the mean was 75 and the standard deviation was 10. Based on the evidence at hand, is the new time slot effective? Use alpha as 0.05. So here is our given. X parallel is equals to 85, which it is our alternative hypothesis, and mean is equals to 75, which is our null hypothesis. So n is equals to 15 and alpha as 0.05. So to get the statistics, we will use this formula. So to substitute it, 85 z is equals to 85 minus 75 over 10 substituted, square rooted, by 15. We will arrive to the answer of z is equals to 3.87. So here in our graph, we will in this area we will find the the alpha. So thus the answer is reject the null hypothesis and accept the new time slot.
Here we have word problem number 4. The following sample of 8 measurements was randomly selected from a normally distributed population, which are 12, 10, 9, 8, 15, 10, 11, and 13. Test for the significant difference between the sample mean and the population mean. The given values are the following. Here we have the population mean of 10 and the significance level of 0.05. Here we also have the hypothesis, which is equal to 10, and the alternative hypothesis, which is not equal to 10. Now for the other values needed to solve this word problem, here we have the standard deviation, which is equal to 10, and the number of members in an equation, which is n is equal to 8. Here we also have the sample mean, which is equal to 11. So the sample mean is calculated by adding all of the values in the sample and dividing it to the number of units. Now in order for us to get the critical value, we need the significance level and the degrees of freedom. Now using the significance level and the degrees of freedom, we can use it to find the critical value based on the table, which is 2.365. Moving on, we will calculate for the t statistic using this formula right here. Now we will first subtract the population from the sample mean, then divide s by the square root of n. Then take the value you got from subtracting the population mean from the x bar and divide it by the value you got by dividing the standard deviation by the square root of n, which is then equals to 0.2857. Lastly, here we have the significant difference, in which we will subtract the critical value and the test statistic, which is 2.365 minus 0.2857, which is equals to 2.0793. Therefore, the significant difference of the sample mean and the population mean is 2.0793 with a 0.95 or 95% confidence level.
Lastly, for item number 5, we have to conduct a t-test with the null hypothesis as mu equals 100, the alternative hypothesis as mu greater than 100, and the alpha as 0.05. We also have the sample mean as 110, the sample as 15, and the standard deviation as 8. Second is we need to use this formula, which we determine that our sample is small. So third, we will substitute our values to the formula, which is 110 minus 100 divided by 8, then divided by the square root of 15, which all results to 4.841. We also have our degree of freedom, wherein we will subtract our sample to 1, 50 minus 1 equals 14. Then using our t-table, we have this result, which we will find out that 1.7613 is our critical value. For step 4, we will determine that
test we are using or we have, since we already found out that this is a left tail test. Applying the value of our degree of freedom, which is 14, then using the t-table, we have our critical value, which is 1.7613 as mentioned earlier. Then we can conclude that our rejection region falls from 1.7613 to infinity. Going back to our value that we got, which is 4.841, this falls in the rejection region, where we find out that if our null hypothesis should be accepted or rejected. Since the rejection region is here and the value 4.841 falls here in this area, therefore we conclude that the null hypothesis is rejected.